Okay, so are you ready to dive into a question that's so big it's been puzzling, like, philosophers and physicists for centuries? What is reality?
And you've come to the right place because we are not just skimming the surface here. We are going deep, deep down into how humanity's understanding of reality has evolved from like ancient Greece to the quantum realm and beyond.
It's kind of like if understanding reality was this mind-blowing museum exhibit.
Oh, I like that.
We're giving you the VIP tour,
Yeah.
hitting the highlights, uncovering those, like, hidden gems that you wouldn't want to miss.
Yeah. And a quick reminder before we get started, when we talk about theories in science, it doesn't mean guesses.
Right, not just, like, some shower thoughts that we're throwing around.
Exactly.
These are, like, powerful frameworks that are backed by evidence and rigorous testing that explain how a huge chunk of the universe actually works.
Exactly. So let's kick things off about like 2,400 years ago with Plato and his theory of forms.
Okay.
Now, you might be thinking ancient Greek philosophy, how is that relevant to my life?
Yeah.
But trust me on this one, it's a classic for a reason.
Yeah, it's surprisingly intuitive.
It is.
Even if you've never, like, cracked open a philosophy book.
Exactly. So imagine you're stuck in a cave, like your entire life, and all you ever see are shadows projected on the wall. Plato argued that those shadows, that's what would become your reality, even though they're just reflections of the real deal.
So we're like those cave dwellers,
Yeah.
kind of mistaking the shadows for the true forms.
Yeah, those shadows are like the world we experience with our senses. They're just like imperfect copies of these perfect, unchanging forms that exist in a higher realm. Think of it this way. The apple you're eating, that's just a fleeting imitation of the ultimate ideal apple that's like existing out there in the ether.
So there's, like, a cosmic apple headquarters somewhere with the perfect blueprint for every apple ever. It's like he's single-handedly inventing the concept of a brand prototype centuries ahead of his time.
Yeah.
But it also, like, makes you question everything you see.
Absolutely.
Yeah.
And that's the beauty of Plato's work. He forces us to question our perceptions. Okay, now fast forward a few centuries, and we meet Isaac Newton, who's busy figuring out why that apple falls from the tree in the first place. Enter Newtonian mechanics, the physics that feels like common sense because
Yeah.
it governs so much of our everyday experience. Like, I set my alarm clock assuming time flows the same for me as it does for everyone else.
Right.
Pure Newtonian thinking.
Yeah.
Newtonian mechanics described a universe like this giant, predictable clock. Every action has an equal and opposite reaction, time marches on uniformly, and space is this fixed stage where everything unfolds.
Until it doesn't, right.
Yeah.
And this is where things start to get really interesting. Enter James Clerk Maxwell and his, like, groundbreaking work on electromagnetism in the 19th century.
Yeah.
He really throws a wrench into Newton's perfectly predictable clockwork universe.
What Maxwell did was huge. He unified electricity and magnetism, which alone was a major breakthrough. But then his famous equations predicted something strange about the speed of light, that it's constant no matter what.
Okay, I'll be honest.
Yeah.
I didn't fully get why that was such a big deal at first. So explain it to me like I'm back in physics class, but you're a way cooler teacher.
Okay. Imagine you're on a train speeding along, right? And you shine a flashlight.
Okay.
You'd think the light from your flashlight would be traveling even faster for someone standing on the platform, right?
Yeah.
Because speeds add up.
Right. That makes sense, yeah.
But Maxwell's equation said, nope, the speed of light is the ultimate speed limit in the universe for everyone. This completely messed with Newton's neat and tidy universe where speeds were always relative.
So something had to give. It's like the universe was telling Newton, nice try, but what was the missing piece of the puzzle?
That missing piece was about to revolutionize our understanding of reality because what had to give way was the very foundation of Newton's universe, our understanding of space and time itself.
Okay, so Maxwell's discovery threw a wrench into things, right?
Mhm.
And it paved the way for, like, arguably the most famous scientist of all time, Albert Einstein.
We got it.
Yeah.
It was Einstein who took Maxwell's work and really ran with it.
Yeah.
What he came up with, his theory of relativity, it was so revolutionary that, like, over a century later,
Oh, yeah.
it still has the power to, like, completely upend how we view the universe.
It's crazy.
It is.
Okay, so let's break it down a little bit.
All right.
Starting with special relativity.
Oh, okay.
What exactly did Einstein mean when he said that space and time were relative?
Well, he realized that if the speed of light is constant, as Maxwell's equations showed, then space and time couldn't be these, like, fixed,
Right.
unchanging things that Newton thought they were.
Okay.
So that meant our experience of time itself
Right.
must be dependent on our relative motion.
Wait, so slow down for a second.
Okay.
Are you saying time isn't the same for everyone?
Yeah,
That's wild.
it is wild.
Yeah.
And it leads to some, like, seriously brain-bending but very real phenomena.
Okay.
One of them is time dilation, which means that time actually slows down for objects that are moving very fast
Relative.
relative to a stationary observer. Yeah.
So if I, like, hopped on a spaceship,
Yeah.
right, and blasted off at close to the speed of light,
Okay.
time would actually slow down for me.
Yeah.
Compared to, like, my friend who's just back on Earth hanging out at the coffee shop.
That's exactly what Einstein's theory predicts.
Wow.
And here's the thing, it's not just a thought experiment.
Right.
Scientists have done real-world tests to prove it. Like, one famous example is the Hafele-Keating experiment, where they flew atomic clocks around the world on airplanes.
Okay.
And when they compared those clocks to the ones on the ground, they found that the clocks that had flown at high speeds were, like, ever so slightly behind.
Wow.
It proved that time really does run a bit slower at those speeds.
See, I knew it was a good idea to become friends with a physicist.
Right.
This is, like, blowing my mind.
Yeah.
Okay, but what about length contraction? I feel like I've read about that in, like, a science fiction novel.
Well, science fiction borrows from real science, and this is one that's, like, definitely strange. It basically says that objects traveling at these relativistic speeds close to the speed of light will actually appear shorter in the direction of their motion from the perspective of someone who's stationary.
So our, like, super fast spaceship, the one I'm hypothetically on, would look squished to someone back on Earth, like a cosmic pancake or something.
Basically, that's crazy.
Einstein's work really showed us that the universe isn't exactly what we thought it was,
Right.
but he didn't stop there. He realized that his own theory, special relativity, had some limitations.
Oh, okay.
It worked great for objects moving at constant speeds, but what about situations where speeds and direction were constantly changing, like acceleration, for example?
Right, because the real universe is a lot more dynamic than things just moving at a constant speed.
Like things are always shifting and turning and falling.
Exactly. And there was another, like, rather important force at play that special relativity didn't account for gravity.
Right, Newton's apple.
Exactly.
So how did Einstein approach that?
Well, he knew Newton had explained gravity as this force acting at a distance.
Right.
But Einstein theorized that gravity wasn't a force at all, but rather a result of the curvature of space-time itself.
Okay, I'm going to need you to elaborate on that one. Give me an analogy, something to help wrap my head around warped space-time.
Sure. Okay, so picture a bowling ball placed in the center of a trampoline.
Okay.
The bowling ball represents a massive object, like a star or a planet.
Okay.
And the trampoline surface is space-time.
Got it.
Now imagine rolling a marble across the trampoline. What happens?
Well, the marble wouldn't go in a straight line.
Right.
It would curve around the bowling ball because it's warping, you know, the fabric of the trampoline.
Exactly.
Okay.
And that's a simplified way to picture gravity.
Okay.
According to Einstein's general relativity, mass warps the fabric of space-time, and
Yes.
that warping is what we experience as gravity.
Wow.
Planets don't so much orbit stars as they kind of fall along the curves in space-time
Oh, wow.
created by the star's mass.
So massive objects create these cosmic divots,
Yeah.
essentially.
Yeah.
Okay.
That's a good way to think about it.
That's actually a really visual way to think about it.
Yeah.
Okay.
Yeah.
But how does this theory of gravity explain things like black holes?
Black holes are, like, one of the most mind-bending predictions of general relativity. They occur when a star is so massive that when it collapses at the end of its life, it creates this region in space-time where gravity is so strong that nothing, not even light, can escape.
It's like space-time gets warped so tightly around a black hole that it essentially becomes like a bottomless pit in the universe.
Yeah, you could say that.
Incredible. Okay, so Einstein revolutionized our understanding of gravity, space, and time. Case closed, right?
Well, not so fast, because while Einstein was busy figuring out the large-scale universe, another revolution was taking place in the world of the very, very small, the quantum realm.
Oh.
And that revolution was about to reveal an entirely new set of rules governing reality.
I'm sensing a but coming.
There's always a but in physics, and this one's a biggie. It turns out that the elegant laws of Einstein's relativity, which work incredibly well for large objects, you know, stars, planets, They break down completely when we get to the level of atoms and subatomic particles.
Wow.
That's where quantum mechanics takes over, and things get really weird really fast.
So the quantum realm, what is it about it that just turns our everyday understanding of reality upside down?
Well, one of the most fundamental concepts in quantum mechanics is this idea of quantization.
Oh,
Imagine trying to, pay for your groceries, but you can only use $100 bills.
right.
No change allowed.
Right.
Sounds a bit tricky, right?
Yeah.
Well, that's kind of how energy works in the quantum realm.
Okay.
It comes in these, discrete packets called quanta pane, not a smooth, continuous flow like we're used to in our everyday lives.
So it's like the universe has this minimum order amount when it comes to energy.
You could say that.
Okay.
And then there's this mind-blowing concept called wave-particle duality.
Okay.
It's the idea that particles, like electrons, for example, can behave like both particles and waves.
So how can something be in two states at once?
That's the thing about quantum mechanics.
Yeah.
It constantly challenges, our classical intuitions.
Right.
Think about how we describe light, right?
Okay.
We say it travels in waves.
Right.
And yet, we also know it's made up of particles called photons.
Yeah.
So, depending on how you look at it or what experiment you're doing, light can show either its wave-like or particle-like nature.
So what you're saying is reality at the quantum level doesn't follow the same rules as the world we experience.
Exactly. And one of the most, fascinating aspects of this is something called the observer effect,
Okay.
which suggests that the very act of observing a quantum system actually influences its state.
Wait, so just by looking at something, we're changing how it behaves?
Yeah, it's one of the things that makes quantum mechanics so intriguing.
That's both amazing and slightly unnerving at the same time.
It challenges our very notion of an objective reality
Right.
existing independently of ourselves.
Wow. Okay.
But here's something else to consider.
Okay.
All this quantum weirdness,
Yeah.
it isn't just some abstract theory confined to a lab.
Right.
It's actually the backbone of much of our modern technology.
Really? So give me some examples.
Yeah.
How does quantum physics actually work its way into our everyday lives?
Well, for one, you wouldn't be listening to this podcast right now without quantum mechanics.
Really?
The transistors in your smartphone, the laser reading information from your hard drive, even the LED lights in your home, they're all based on our understanding of how particles behave at the quantum level.
Wow, that's incredible. Something can be so mind-bogglingly strange, but also incredibly practical at the same time.
Exactly.
Okay, so let's get back to the rules of reality.
Okay.
So far, we've got Einstein's theories explaining the big stuff, gravity, space, and time, and then we've got quantum mechanics describing these tiny details of the subatomic world.
Right.
Did anyone ever try to bring those two together?
Yeah.
To find a single elegant theory that could explain it all?
They did. And it's one of the biggest challenges in physics today.
Right.
You see, as elegant and powerful as Einstein's relativity and quantum mechanics are, they don't always play nicely together.
Right.
That's where we get into the search for a unified theory, something often called a theory of everything.
A theory of everything, it sounds almost mythical.
Mm.
So what are some of the contenders for this, ultimate explanation of reality?
One leading candidate is string theory,
Okay.
which suggests that the universe isn't made up of these point-like particles,
Right.
but rather these tiny vibrating strings of energy.
Okay, so now we're getting down to the nitty-gritty of the universe here.
Yeah.
Strings that are so tiny that they make atoms look massive.
Yeah. Think of it like this. If an atom were the size of our solar system, a string would be about as big as a tree.
Wow, that's tiny. Okay, so how does this string theory help, tie everything together?
Well, string theory suggests that the different vibrations of these strings are what give rise to all the fundamental forces and particles we observe,
Okay.
including gravity.
Wow.
It's an incredibly complex theory, though,
Okay.
and it requires the existence of extra spatial dimensions that we can't even perceive directly.
Extra dimensions, beyond, up, down, left, right, forward, backward.
Exactly.
Now, that's a concept that captures the imagination.
Yeah.
But what about other approaches? I mean, are there other ways to try to unify these forces?
Yeah, there are.
Okay.
Another promising avenue is something called loop quantum gravity,
Okay.
which suggests that space-time itself isn't this smooth and continuous thing as we perceive it, but rather it's made up of these tiny, indivisible chunks,
Okay.
kind of like pixels on a computer screen.
So instead of a seamless fabric of reality, it's more like reality is pixelated at these smallest levels.
In a way, yeah.
That's wild. And these are just two examples, right?
Yeah, exactly.
There's a whole bunch of other theories out
There's
there
a whole landscape of fascinating theories out there, yeah.
that are all trying to reconcile these fundamental forces and give us this, like, more complete picture of the universe.
Exactly. And, like, who knows what breakthroughs await us in the years to come, you know?
It's true.
Just such an exciting time to be thinking about these questions.
I have to say, even just exploring these ideas with you today, it really makes you realize just how much we don't know about the universe.
It really,
But that's part of what makes it so fascinating, right?
absolutely, the mystery keeps us going, keeps us asking these questions.
If this deep dive has left you with more questions than answers,
Yeah,
that's a good thing, right?
absolutely.
It means you're starting to see the universe with a sense of wonder and curiosity.
I love that.
Keep questioning, keep exploring, and maybe, just maybe, you'll be the one to unlock the next big secret about reality.
I like it. The quest continues, right?
Exactly, the quest continues.